Before we move on to the next lecture on turbulent internal flows, let's just take a quick look at a sidebar, which is of relevance and interest to us. In the previous lectures, it was shown that for turbulent boundary layer, both over external or in the case of external flows as well as internal flows, there was a universal structure in the form of a viscous sublayer and then a logarithmic overlap layer. This was shown to exist for all Reynolds numbers using experimental data. In the same manner, it has been shown through experiments that a similar universal structure exists in the case of boundary layer flow due to natural convection. So the only difference between this and the previous case is that in the previous case the flow was isothermal, meaning temperature remained constant, and in this case the temperature varies as a result of natural convection. And in the previous case, the governing parameter was the Reynolds number, whereas in the present case, the governing parameter is the Grashof number, denoted GR. It was shown through extremely careful experiment, which actually was a landmark experiment by Suji and Nagano. These were Japanese researchers in the mid 1980s. That for these ranges of Grashof numbers, the boundary layer, the mean velocity, showed a universal structure. You can see the collapsing of the data from these two experimental data curve. You can see the collapsing of the data for x plus or y plus less than 10. Now, in 2006, Lattice Boltzmann numerical simulation by my MS student Harish Dixit corroborated for two values of Grashof numbers, which are 1.76E8 and 1.76E9. These corroborated the existence of this universal structure in the natural convection case and extended the region of validity of this universal structure. So it's quite interesting to see in this case that experiments showed the existence of such a universal structure first, and later ab initio numerical calculations were able to confirm this existence and also extend the range of validity of the existence of these structures. Let us now move on to turbulent internal flows. What we will be looking at in this lecture and possibly in the next lecture would be turbulent flow through pipes. In other words, the turbulent counterpart of the Hagen-Poiseuille flow. Now, turbulent flow through pipes is a ubiquitous application in the sense that we encounter it in our everyday lives in many different forms. For instance, flow of water in pipes in our houses, flow of water in the buildings that we occupy, flow of water or pumping of water from the municipal pumping station to our house through underground pipes, and the transport of water from lakes and reservoirs to the municipal pumping houses again through pipes. And in other interesting cases, applications such as pumping of crude oil from oil fields to crude oil processing plants, and also transport of processed oil from processing plants to shipping land, to shipping terminals and so on for further transport to other parts of the world. So, turbulent flow of fluids in pipes is an ubiquitous application. And so what we are going to do now is to actually try to see how to determine pumping power required for carrying a certain amount of fluid through a certain head in such situations. That is the engineering problem that we are interested in. So we want to lift the fluid through a certain head, and we want to maintain a certain flow rate, and the flow is turbulent. So how much pumping power is required to accomplish this? That would be our end goal. Now, in our previous lecture, we actually looked at experimental data for turbulent flow inside pipes reported by Nukradze as well as Lindgren. And we commented on the fact that in this case, the logarithmic overlap regions extend so far. For example, it extends up to y plus of almost 10,000 or sorry 100,000 in this case. So Nicarag's experiment covers Reynolds number from 4,000 to 3 about 3 million or so. And as you can see, the logarithmic overlap region in these cases extends almost up to 100,000, 1 plus of 100,000. And experimental data by Lindgren, which was taken later, shows that the logarithmic overlap layer extends to about 800 or so. And then beyond that, we actually have the outer layer or the so-called wake region, where once again, the flow shows a certain universal structure. It's looking at these two data and looking at how small the wake region actually departs from the logarithmic profile. Notice that the deviation of this outer region from the logarithmic profile is very, very small. So considering this and this, it would probably be more appropriate to say that there is actually no wake in the case of wake or outer layer in the case of internal flow when compared to external flow, where the outer layer is distinctly different for different types of flow. So you can clearly see that the logarithm region extends to very high values of wall wipers with practically no outer layer at all. So here it goes up to 900, here it goes up to 100,000 or so, with practically no outer or wake region at all. So this allows us to start with the following claim. So we say that the log law profile in the case of turbulent pipe flow, the log law profile for the mean velocity approximates the velocity profile all the way from the wall to the center line. So we make this claim based on experimental data that was just discussed. So we say that the velocity profile looks like this. So this is the log law profile as we know, with the constant kappa equal to zero point 0.4 and b equal to pi of 8.5. Notice that here this W actually denotes the turbulent mean velocity in the pipe and not instantaneous velocity. The over bar has been dropped here for the sake of convenience, but this denotes the turbulent mean velocity in the pipe, because otherwise we would not be able to use this log law at all had it been instantaneous velocity. And that is important to note because we will be using the over bar to denote average velocity as we had done in the past from now onwards. Now, knowing this velocity profile, we can now proceed like this. The average velocity, which is nothing but the volume flow rate divided by the cross-sectional area, may be evaluated by integrating through each incremental cross-sectional area like this, and we end up with an expression that looks like this. So this involves the friction velocity, which is square root of tau wall divided by rho. Now, it may be recalled that in the context of Hagen-Poiseuille flow, we had actually derived this relationship and said that this is applicable to both laminar as well as turbulent flow. Let us just quickly see where this relationship came from. So if you look at a control volume like this, then the frictional force on the walls of the control volume may be written as tau wall times 2 pi r times L, which is the lowercase l, which is the length of the control volume. This is balanced by the pressure forces on these two faces of the control volume. So the pressure difference between the two faces may be taken as delta P. So the net pressure force on the control volume is delta P times the cross-sectional area pi r square. So if we balance these two forces, then we end up with this expression. And so based on this, if you use the fact that the friction velocity is square root of tau wall divided by rho, you may actually rewrite this like this. So W star may be written in terms of the friction factor and the average velocity. And the quantity inside the logarithm here, R W star over mu, may also be rewritten in terms of the Reynolds number based on the pipe diameter and the friction factor. Now, if we substitute these two into this expression, then we end up with an expression that looks like this. 1 over square root of x equal to 2.0355 logarithm of this minus 0.9132. Now, Prandtl obtained this expression first, and we rearranged this constant so that this one read as 2, and this one was rewritten as 0.8. So it may be written in a more compact form like this. And this is known as the Prandtl's universal law of friction for turbulent flow in smooth pipes. And because we have used this profile to start with, and this profile we have shown to be valid to experiments for Reynolds numbers up to 3 million or so, we can essentially state that the Prandtl's universal law of friction is valid for arbitrarily large Reynolds numbers. So there is no Reynolds number range of Reynolds application or validity of Reynolds number for this particular expression. So that's why it's called the universal law of friction for friction factor in smooth pipes, turbulent flow in smooth pipes. And you can also see if you calculate the value of F for different values of Reynolds number, notice that this is an implicit relationship. So F appears on both sides. So if we solve for F for different values of Reynolds number, F looks like this. And of course, it's clear that F is from this functional form itself, it is clear that F depends only on the Reynolds number like its laminar counterpart, which depended only on the Reynolds number. The friction factor for turbulent flow in a smooth pipe also depends only on the Reynolds number. Can we see that the friction factor decreases with the Reynolds number? However, the pressure drop depends upon W bar square. It may be recalled that the pressure drop delta P is F times L times W bar square over 2D. So W bar square depends on Reynolds number as Reynolds number square. So although the friction factor decreases with Reynolds number, the overall pressure drop still increases in Reynolds number in the case of turbulent flow in smooth pipes. Now, in the case of turbulent flow, in contrast to the laminar situation, the roughness of the pipe actually has a tremendous effect on the friction factor. In laminar flow, of course, there is no question of the roughness having any effect at all. So in this case, the roughness has an effect, and that is what we are going to explore next. Lukuradze, who was one of Prandtl's students, carried out a series of experiments, very careful experiments, landmark experiments to investigate the effect of roughness in 1933. So he basically glued very carefully chosen sand grains of uniform size on the inside surface of the smooth pipe to simulate the effect of wall roughness, and he measured the pressure drop as well as the velocity profile in these so-called rough pipes. Now, in this case, we can reasonably expect the friction factor to depend on the roughness, which is characterized by this grain size epsilon, and also on the Reynolds number. For the smooth pipe, the friction factor depended only on the Reynolds number. Now we can expect it to depend on the roughness also, in addition to the Reynolds number. Let us see how this relation or what this relation looks like. So Nicoraz's experimental data showed that as a result of the presence of the roughness, the velocity profile was simply shifted down by a certain amount. So this is the velocity profile when the pipe is smooth, and the presence of the roughness simply shifts velocity profile down by a fixed amount like this, as can be seen here. So this is the law of the wall for smooth pipe, and the roughness actually keeps shifting this law of the wall further and further down. But he also calculated from his experimental data the amount of the shift. The shift is zero when the roughness was such that epsilon plus, which is nothing but epsilon times W star divided by nu, is when it is less than or equal to 5, we may consider the pipe to be smooth. And if epsilon plus is greater than 70, then the downward shift was given by this amount, and this could be considered to be fully rough. So this was what he said. The pipe is smooth, which is in this region, epsilon plus less than 5. That is, as you can see, y plus less than 5 in this region. The pipe may be considered to be smooth without any downshift of the velocity profile. And in this region, when epsilon plus becomes more than 70, so we can see that this dashed line corresponds to y plus of 70. And when epsilon plus becomes higher than 70, then the pipe may be termed to be fully rough. Now, in the case of the fully rough situation, knowing this delta B, we can write this velocity profile and then try to get an idea on what it looks like. But before we do that, let us just give a description of these three regions. So we have now seen three regions when roughness is present. So in the first regime, which is the hydraulically smooth regime, the roughness is such that epsilon plus is less than 5. And in fact, the roughness is so small that it is contained within the viscous sublayer. So it plays no role at all, and it can be treated as a smooth pipe, and the friction factor depends only on Reynolds number as shown earlier. Now, in the transitional regime, where the epsilon plus or the roughness is such that epsilon plus lies between 5 and 17, the wall roughness actually partly protrudes over the sublayer. It does not protrude entirely, but it partly protrudes over the sublayer. So in this case, the pressure drop in the pipe, which until now was only due to viscous drag, is also due to form drag due to the protrusion of this roughness above the sublayer. So now the total pressure drop is due to the sum of viscous drag in the pipe plus form drag due to the protruding roughness above the sublayer. Okay, so it is due to both, and the friction factor in this case just depends on both the effects. One is the Reynolds number, so the viscous pressure drop or pressure drop due to viscous action depends on Reynolds number, and the pressure drop due to the form drag from the protuberances depends on epsilon over d. So the overall friction factor depends on these two quantities. Now, in the fully rough regime, where the roughness is so big that epsilon plus is greater than 70, then it actually protrudes almost entirely above the sublayer, and consequently the sublayer is completely broken up. So in this case, the pressure drop in the pipe is almost entirely due to form drag of the roughness of the protuberance, and so there is no significant pressure drop due to viscous effect, which means that the dependence of friction factor on Reynolds number is no longer seen because the pressure drop due to viscous effect was accounted for through the Reynolds number, and when the roughness is so large then there is no viscous effect and the pressure drop is entirely dominated by the form drag due to the protuberance. So the dependence of the friction factor on the Reynolds number is completely absent in the case of fully rough regime, and the pressure drop or the friction factor depends only on the size of the rough. So in this regime, as can be seen, the friction factor depends only on the size of the roughness. So to summarize, in the hydraulically smooth regime, friction factor and pressure drop depend on Reynolds number because the pressure drop is entirely due to viscous effect. In the transitional regime, friction factor and pressure drop depend on the roughness as well as Reynolds number because the pressure drop is due to a combination of viscous effect plus form drag due to the roughness which partly protrudes out of the sublayer. Now, in the fully rough regime, the pressure drop and the friction factor depend only on the roughness because the pressure drop is entirely due to form drag of the roughness of the protuberances, and very little of it, or there is very little contribution to the pressure drop from viscous effect. Now, in the fully rough regime, as we had already shown, we know delta V, and we also know this velocity profile. So we can combine these two and write the velocity profile in the fully rough regime like this. So this is the smooth, the expression for, log law expression for smooth pipe plus a delta V. And in a fully rough regime, the delta V is given by this value. So we can combine these two and write W over W star equal to this. Notice that the W star on the right hand side is absent now after combining these two. And if we follow the same strategy as we did before for a smooth pipe, namely calculating W bar, then using this expression to come up with an expression for friction factor, we can now, in the fully rough regime, we can obtain an expression for friction factor that looks almost like what it did before. So now 1 over square root of F equal to minus 2 log epsilon over D divided by 3.7. So we now have an expression for friction factor in the case of hydraulically smooth regime from Prandtl's universal law of friction, and we also have an expression for friction factor in the fully rough regime, which looks like this, and the Prandtl's universal law of friction looks like this. So we have this expression and we have this expression. Now Colebrook in 1939 combined these two and then wrote them as a composite expression which looks like this. And there is no equation as such for calculation of the friction factor in the transitional regime. This one may be used to calculate the friction factor in the fully rough as well as smooth flow regime. So Moody calculated friction charts, Moody calculated friction factors using this expression. And this was then presented in the form of a chart, which is famously known as the Moody's chart. Okay. Now, in case the geometry that we are looking at is non-circular, the diameter d here can be interpreted as the hydraulic diameter, and we can proceed to calculate friction factor using this expression. So if you actually plot the data of for friction factor in Moody's chart, the variation looks like this. Notice that the laminar region lies here, the Reynolds number, maybe less than 2000, 2400 or so. And this is given by 64 over RE based on diameter. And we see the transition region here where there are no expressions for calculating friction factor. And now we see here the smooth pipe. This corresponds to this curve corresponds to turbulent flow in smooth pipe. And then as we go up here, there is increasing roughness. Then once we go beyond this, we go into the fully rough zone. Notice that the size of the roughness increases as we keep going like this. So the roughness is below 10 raised to minus 5, epsilon over d 10 raised to minus 5. We can consider it to be smooth. And as the roughness increases, the epsilon plus also increases. And beyond a certain value, the pipe becomes fully rough. Notice that once the pipe becomes fully rough, the fully rough region is delineated by this dashed line. And in the fully rough region, it is clear that the friction factor remains a constant and depends only on epsilon over d and not on the Reynolds number at all. So for any Reynolds number, it can be seen that friction factor remains the same and it changes, for example, from here to here only with the roughness and not with the Reynolds number at all. Whereas in this region, it can be seen that the friction factor changes with Reynolds number as well as roughness. So this is the region lying in between the fully rough and the fully smooth region. Some values may be evaluated in this region also. There is no values are available in this region. Now, as I said earlier, the primary objective of doing these types of studies is actually to be able to calculate the pumping power for a particular application. You mentioned many applications in relation to turbulent internal flows, and the primary objective is to be able to calculate the pumping power. Okay, so we can easily calculate the pumping power as the product of rho g times delta y plus hf. So again, delta y is the gravity head, hf is the head loss due to friction multiplied by the flow. So we had derived this expression earlier or in connection with Hagen-Poiseuille flow, and this remains the same. The only difference is in the manner in which hf is calculated for laminar flow or for turbulent flows. Now, in a particular application, we may wish to pump water from one location to another location, which is, let's say, at a higher level or a lower level, it doesn't matter. So delta y is known. And if we are given the length of the pipe and the diameter and the volume flow rate and the roughness, we can calculate the head loss and the pumping power. But in reality, what generally happens is that not all these quantities are known. For example, when we have to select a pump for a particular application, the pump has its own characteristics. So, for example, for a given power, the pump can develop a low head but with high flow rate, or high flow rate but with a low head. So for the given problem, choice of a pump depends on the theoretical depends on the characteristic of the pump itself. Okay? So now, since the head loss due to friction itself depends on the flow rate, being high with higher flow rate, and so on, selection of a pump for a given application using the characteristic of a pump becomes an iterative exercise. So we start with an assumed value for, let's say, head loss due to friction, and then we determine the Q that we can obtain for a given power. Then we keep going until the head that is developed by the pump matches the Q that it efficiency of the pump is also usually available from the pump characteristic. So this is the theoretical power. We can then divide this by the efficiency of the pump to get the actual power that is required to accomplish the stated objective.